Welcome, nocturnal minds aboard. Your learning journey starts now. Right. So we've just explored how symmetry principles can lead us towards a kind of similarity in truth. Now, let's broaden our lens and look at another big idea that's been driving science forward: unification. Think about it, from the ancient Greeks wondering if everything was water to Plato trying to unify knowledge, belief, and value through his forms, or Pasteur linking microbes to disease. People have always craved not just facts, but connections between them. It's like being a cosmic detective finding out how all the pieces of the puzzle fit together. Even today, physicists are obsessed with unifying the fundamental forces. They call it the Holy Grail. Some even argue that explanation itself is a form of unification. But here's the kicker. What exactly does unification mean? Is it just nice to have, or is it the very engine of scientific understanding? So, if we want to get serious about unification, we need to untangle this concept. Because honestly, when scientists talk about unifying something, they might be talking about totally different things. Imagine trying to categorize all the ways you could connect two seemingly unrelated dots. It's a bit messy, but Todd Jones suggests a helpful framework, dividing unification into two main families. First, there's subtype and similarity, or SS. This is about showing that different things are actually related because they share some kind of similarity or belong to the same broader category. Think sorting socks. Second, there's conjunction and coordination, or CC. This is about showing that different things interact, connect, or coordinate with each other, even if they aren't inherently similar. Think building a bridge connecting two islands. These two families capture the essence of how we try to make sense of a complex world. Let's dive deeper into the CC family first. This is all about connections and interactions. At its weakest, CC unification is pretty straightforward, grouping things just because they happen to be next to each other. Think calling a bunch of nearby mountains the Appalachians, or referring to a long series of battles as the 100 Years' War. It's a label for proximity. But then you get strong CC unification, where things are genuinely linked functionally. Think of your body's endocrine system. The hypothalamus, pituitary, adrenal glands don't just exist side by side. They work together, influencing each other in a coordinated way to produce effects. Like waking you up with an alarm clock made of hormones. And then there's the moderate stuff, discovering a causal link between things that weren't obviously connected before. Like realizing that carbon dioxide emissions cause polar ice caps to melt. Anytime you find a relationship, even between dissimilar things, you're doing some kind of CC unification. It's everywhere in science. Now, let's switch gears to the SS family, subtype and similarity. Here, the focus is on showing that different things are fundamentally related because they share characteristics or belong to a common category. The strongest form here is reductive identification, where you show that two things are actually identical. Maxwell's work showing light isn't just related to electromagnetism, but is electromagnetic radiation. That's a classic example. It's like realizing your pet rock is actually a rare meteorite, ontologically simplifying by showing identity. On the flip side, there's minimal SS unification, which is just about feature sharing. Showing that both dolphins and pigs are mammals, because they share certain properties like having hair, giving birth to live young, etc. Or as Hogan found, that both the energy distribution of gas atoms and income distribution in developed countries follow an exponential pattern. It's about finding common ground in features. There's even a weaker version, where things are grouped based on resemblance to a prototype, maybe not sharing a single defining property, like how Gould discusses the class fish: lots of similarities, but no single gene or trait defines all fish. So, how do we decide if things are similar enough for SS unification? Well, there are tons of ways. Think about the word vertebrate. We unify all those animals under one umbrella because they share the internal property of having a backbone. Simple enough. But what about gene? Being a gene isn't defined by its internal structure necessarily. It's often defined by its external functional role, what it does, like producing certain effects during development. Lots of different molecules can act as genes in different organisms, multiply realized properties, as philosophers call them. Then there's similarity based on holistic structure, like the Hardy-Weinberg equation describing population genetics across vastly different species. Or a similarity based on quantity, like saying plants of different types all show reduced chlorophyll at a specific growth stage. You can even unify things based on family resemblance, like marketing research grouping people with similar purchasing habits. Or shockingly, by what they lack. Describing someone as autistic who lacks empathetic understanding. The point is, there are as many ways to find similarity and create these SS unifications as there are clever ways to categorize the world. Now, here's where it gets really interesting. Often, scientists aren't just doing one type of unification, they're juggling both SS and CC at the same time. Take chemistry, you understand ionic bonding, see how sodium and chlorine atoms interact and coordinate. But you also make an SS identification, recognizing the resulting compound as sodium chloride or salt. It's both the process and the product. Another great example explaining why the sky is blue. You bring together optics, chemistry, meteorology, biology. CC tell a story about light, the atmosphere, particles, wavelengths, and our eyes. But to even start that story, you first needed SS unifications to grasp concepts like atmosphere, a collection of nitrogen and oxygen, particle, so you knew what to connect with ideas from other fields. It's like needing to know what a car is, SS, before you can explain how the engine, transmission, and wheels work together. See? This constant interplay makes pinning down exactly what scientific unification means so darn tricky. So far, we've mostly talked about metaphysical unification, figuring out how things in the world are connected or similar. But the idea of unification extends beyond just describing reality. There's epistemic unification, which is about bringing different methods of investigation and reasoning together. Think of Popper's idea that science revolves around falsification, a specific method. Epistemic unification could be showing how different methods work well together, like using observation and experiment in tandem. Then there's normative unification, which deals with the goals of science. Van Frassen, for instance, argued for unifying the aims of science under the goal of developing empirically adequate models. Both these epistemic and normative forms can also be broken down into SS and CC types. SS, epistemic, might show different tools are similar, while CC epistemic shows how they work together. Same logic applies to normative values. This multi-layered view helps explain why so many diverse activities get lumped under the banner of unification. Okay, so we've seen the different flavors of unification. But why bother? Why is this such a big deal in science? Well, one incredibly practical reason, highlighted by Ernst Mach and others, is that unification is basically a cognitive cheat code. It saves our brains and our collective memory banks precious resources. Think about it. When things are linked via CC unification, like understanding the Krebs cycle, your brain builds an associative network. Need to recall what happens after two carbon atoms are oxidized. Boom, quick access. It's like having a super efficient search engine for facts. And it saves space too. If X correlates strongly with Y, you don't need to store every instance of both. Knowing X tells you about Y. With SS unification, classifying all carbon atoms as one type lets you store info about carbon once, instead of having a massive redundant representation wherever carbon appears. Searching categorized information is way faster than sifting through random facts. Ultimately, unification lets us handle way more information, makes us smarter agents, and crucially, reduces the number of brute facts, things we just have to accept without explanation. Who doesn't love that? Now, some thinkers take this idea of unification even further. Figures like Huxley, Friedman, and especially Philip Kitcher argue that unification isn't just a good thing for science, it is the core of scientific explanation. Kitcher's theory is quite sophisticated. He starts with the standard idea that explanations are like deductive arguments ending with the fact we want to explain. But here's his twist: an account is only truly explanatory if it fits into a specific pattern. First, it must be an instance of a general schematic derivation pattern, a recipe for generating conclusions. Second, this pattern must be part of the explanatory store. What's the explanatory store? It's the minimal set of such patterns that together can generate the maximum amount of our total knowledge. Think of it as the most powerful concise toolkit for understanding the universe. By deriving facts using this sparse toolkit, we show how many different facts stem from the same underlying principles. Explaining something on this view means showing how it fits into this best possible, most unified understanding we can muster. But hold on, not everyone buys this unification equals explanation idea. Many philosophers, particularly those who emphasize mechanisms, think the real heart of explanation lies in revealing the underlying causal processes that make things happen. They call this the ontic view, focusing on the actual stuff causing events. They argue that the unification view, being epistemic, focuses too much on patterns and correlations, and misses the real why. Think about explanatory asymmetry. Why does knowing the sun's angle and tower height explain the shadow length, but not vice versa? Hempel's deductive nomological model struggles here. The ontic view often points to causal mechanisms as the key. Plus, there are deep worries. How do we know we've found the right causal mechanisms? Hume famously questioned our ability to even grasp causality. And if multiple theories can equally unify data, how do we choose? The ontic view says, look for the one, revealing the true mechanism. The unification view counters, choose the one that best systematizes our knowledge. How do the unificationists respond to these challenges, especially the asymmetry problem? They actually say, hey, asymmetry isn't really a problem for us. Let's revisit the shadow example. Yes, you can derive shadow length from height and angle, and height from shadow and angle. But consider another pattern, the origin and development pattern. This involves knowing the designer's intentions or historical context to figure out the height. This pattern can potentially derive the dimensions of almost any structure, unlike the shadow method, which fails for transparent or non-casting objects. Since the origin and development pattern is more general and powerful, it derives more facts. It would be part of the preferred explanatory store. Therefore, the derivation based on intention is the explanatory one, not the shadow calculation. Similarly, for Barnes' fossil case, even if we can derive dinosaur existence from a fossil, maybe we lack a competing theory explaining why that specific skeleton evolved. Unificationists argue that even if the fossil derivation seems weak, there's likely a Darwinian evolution pattern in our explanatory store. We might use it speculatively or partially. The point is, we don't necessarily prefer a more complex derivation just because it uses more patterns. The goal is maximizing the range of conclusions from the fewest patterns. Okay, so the unification theory has some clever responses. But it still faces hurdles. A major one is, how do you choose between different unifying accounts? Imagine you have two competing theories. One explains slightly more facts but uses twice as many derivation patterns. Another uses half the patterns but explains fewer facts. Which is better? Current versions of the theory don't give us clear rules for balancing these trade-offs. You could tweak the scoring system endlessly. 5 plus 5 plus 5 equals 15. 5 plus 6 plus 4 equals 15. 5 plus 5.000, 1 plus 4.9999 equals 15. And always find a slightly better score. How do you pick the winner? Furthermore, there's the worry that a systematization leading to an intuitively weird or non-explanatory account might actually be more unifying than one leading to an intuitive one. For example, maybe a bizarre theory perfectly fits all data with one simple pattern, while a common-sense theory needs 10 complex ones. Unificationists need to convince skeptics that such scenarios either don't occur in practice or that additional principles can rule them out. Otherwise, the link between unification and intuitive explanation remains shaky. So, wrapping up the unification discussion, it's clear that unification is a hugely important goal in science. We've seen it comes in many forms, from simple grouping to complex functional integration. These different types often blend together in practice. The big question remains open: is unification the secret sauce of science, the very mechanism by which we achieve and recognize genuine explanations? That's a hot debate, and it seems we're still figuring it out. For those interested in digging deeper into the nuances of unification, this slide provides a curated list of key readings. From Mack and the Vienna Circle laying groundwork, through critiques by Fodor and Galison, to the major works by Friedman and Kitcher, and subsequent defenses and refinements by Jones and others, plus critical perspectives from Hallinan, Hintika, Woodward, Jaspers, Salmon, and Strevens. A rich landscape for further exploration. Alright, shifting focus now. Having discussed how we seek unity in knowledge, let's turn to how we judge the quality of the theories themselves. Scientists are constantly evaluating observations, generalizations, and especially theories. What makes a theory good? Sounds simple, right? But ask 10 scientists, and you'll likely get 11 different answers. This question has been around forever. Think back to early astronomy. Aristotle had his complex system of spheres explaining how planets moved, while Ptolemy built incredibly accurate mathematical models predicting their paths, but harder to interpret causally. Which was better, the explanatory elegance of Aristotle or the predictive power of Ptolemy? Copernicus tried to bridge them. Kepler pushed for explanatory appeal alongside accuracy, and Galileo focused on observable regularities, while Descartes delved into speculative causal structures. This tension gradually led to distinguishing between laws, describing what happens, and theories explaining why. As the mechanical philosophy took hold in the 17th century, thinkers realized their theories were getting increasingly hypothetical, tiny corpuscles, invisible ether vortices. Boyle explicitly listed requisites for a good hypothesis, including internal consistency, coherence with other physics, avoiding ad hoc fixes, and simplicity. Huygens also emphasized the desirable features like generating novel predictions. Locke even pondered how relying on theory would change the nature of scientific knowledge. The message was clear back then: just fitting the data wasn't enough. Science aimed higher, needing other criteria to guide it towards deeper understanding. This awareness wasn't lost on the pioneers, even if later empiricist trends sometimes obscured it. This brings us to Thomas Kuhn and his reaction against logical positivism. Positivism tried to make science purely logical and based solely on observation statements, treating theory as secondary and problematic. Kuhn looked at the messy reality of science, full of controversy and paradigm shifts, and argued that theory assessment is far more complex. Initially, in The Structure of Scientific Revolutions, he suggested that scientists try to maximize a set of different values, and these values can even change depending on the prevailing paradigm. It's not rule-based, but value-laden and judgmental. Later, facing criticism about whether this allowed for rational science, Kuhn revised his stance. He argued that certain values like accuracy, scope, fruitfulness, and later simplicity and consistency are permanent attributes of science, guiding rational choices even through paradigm shifts. These became the bedrock for assessing theories. Let's start cataloging these virtues. The most fundamental one is empirical fit. Pretty straightforward, right? A theory's got to account for the data we already have. If it doesn't explain the phenomena it's supposed to explain, it's pretty much dead on arrival. Of course, small deviations can be tolerated, especially when a theory is brand new. But as anomalies pile up, that's when the pressure mounts to modify or ditch the theory. It's crucial to distinguish this from Van Frassen's idea of empirical adequacy. That means all consequences of the theory are true, which is basically a promise we can never fully verify. Empirical fit is about what we can check against reality. Sometimes people list explanatory power as a separate virtue. But McMullen argues it's not really independent. A theory's power to explain depends on all the other virtues working together. If it lacks empirical fit, or is internally inconsistent, or doesn't mesh well with other theories, it's going to be a poor explanation. When explanatory power is mentioned, it might refer to how convincing the proposed causal structure is, how well it aligns with our general intuitions about cause and effect. But even then, this likely boils down to other virtues like internal coherence or optimality. So, let's keep it simple. Explanatory power is the result, not a separate input. Next up, internal virtues. These are about the theory standing alone as a logical construct. The absolute must is internal consistency. A theory riddled with contradictions is useless, even if it accidentally predicts something right now. It could blow up later. Inconsistency can hide in plain sight, like smuggling in an unacknowledged premise. Then there's internal coherence, or the absence of ad hoc features. Remember Ptolemy's epic cycles? He added them just to make the math fit the data, seemingly arbitrarily. Kepler thought that was a problem, a coincidence begging for explanation. Empiricists might shrug, coincidence happens. But lack of coherence counts against a theory. And then there's simplicity. Ah, simplicity. Everyone loves it, but nobody agrees on what it is or why it matters. Is a simpler theory automatically better? Maybe sometimes, maybe not. It's context-dependent, aesthetically pleasing, practically useful, but hard to pin down epistemically. Given the debates, McMullen suggests we might be better off not listing it as a distinct, universally recognized virtue in the core assessment toolkit. Moving on to contextual virtues. Theories don't exist in a vacuum. They live within a larger web of ideas. First, external consistency, or consonance. Does a theory play nicely with other established theories? Level E, does it align with physics if it's a chemistry theory? Level R, does it clash with deep metaphysical principles like causality? Level N, does it match with social or political values? Historically, scientists tried to ignore these, calling them idols. But recent discussions question if ignoring them is always wise, blurring the lines between epistemic and non-epistemic factors. Then there's optimality. This is about comparing theories. Is this the best explanation available, given the alternatives? This requires looking beyond the intrinsic merits of one theory to see how it stacks up against rivals. It's a partially extrinsic virtue, but a real one nonetheless. Finally, the diachronic virtues. These are the ones that only reveal themselves over time, as the theory's career unfolds. They're the virtues that scream, this theory is likely approximating reality. Because they show resilience and growth. Instrumentalists and strict empiricists often downplay these. Three key diachronic virtues stand out: fertility, consilience, and durability. Fertility means the theory keeps producing new insights. Novel prediction is the poster child. Successfully predicting something unexpected lends huge credence to the theory's underlying structure. Meeting anomalies head-on, suggesting modifications, or elaborating the causal structure over time, like how our understanding of the atom grew from a simple ball to a complex nucleus and electrons, also shows fertility. Consilience is the power to unify disparate phenomena over time, like Maxwell uniting electricity, magnetism, and light. And durability is simply surviving tough tests over a long period. These virtues, McMullen argues, are the ones that truly distinguish science aiming for truth from mere instrumentalism. Why does this focus on diachronic virtues matter? Because it hits at a fundamental divide in philosophy of science going back to Hume. On one side, you have anti-realists who see science as just providing useful tools and formalisms for prediction and control, not necessarily reaching towards an unobservable reality. Think instrumentalism, logical positivism, or some social constructivist views. On the other side, realists believe science uses observable regularities as a stepping stone to uncover hidden structures and causal truths. Most scientists lean realist. Where do they clash? Exactly on the diachronic virtues, especially novel prediction. For anti-realists, if you're just evaluating a useful tool, does a novel prediction really matter more than fitting existing data? For realists, yes, a successful novel prediction strengthens the claim that the theory reflects reality, boosting its overall status, including its predictive power. This debate often hides a deeper disagreement about whether theoretical entities even have a claim to truth. So, should we embrace these virtues, as Kuhn called them, permanent attributes of science? McMullen leans heavily towards yes. Their track record is undeniable. They've guided science to remarkable discoveries about the hidden workings of the universe, the large, the small, the distant past. Perhaps the biggest achievement of science isn't any single discovery, but figuring out how to do science well. And these virtues, these expectations about what makes a good theory, have been crucial in shaping that success. And finally, for those wanting to explore the virtues debate further, this slide offers a selection of key texts. From Herschel and Well reviving the discussion through Lakatos emphasizing novelty, Friedman highlighting unifying power, Van Frassen challenging non-empirical virtues, Kukla defending them, Thelos championing realism, and Longino exploring the social dimensions. A fascinating area of ongoing philosophical inquiry.